Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about the Flat Earth Society and those that believe that the Earth is flat and not spherical. And once again, this is an enrichment lecture, so you will not see this covered directly in the textbook. But it is something that I find interesting enough to include here in the lecture videos. So let's go ahead and get started. And why do we look at this? One question sometimes that I get is, why are we looking at this in an astronomy class? You will find essentially no astronomers who believe that the Earth is flat. So I think that in many cases it is still important to understand other ideas, even if as an astronomer we know that they are wrong, and gives us a better way to understand the reality of the universe. Now, just to say this, I understand that there are many different versions of those who believe in the flat earth. They don't all believe exactly the same things. So I'm going by what I have learned by studying some of their ideas, reviewing different websites and discussions with people as to what their beliefs are. So I'm not being able to hit on every single belief that those who believe in a flat earth follow, but I'm trying to make some kind of points on it and just a little bit more understanding of what is going on. So what are my thoughts? Well, as an astronomer, yes, I believe that the Earth is spherical. And this has been proved by observations from NASA and others. But so just because I am discussing flat earth arguments here does not mean I am endorsing them or saying that they are correct or that they should even be considered reasonable. But it is still important to look in any debate to look at both sides. If you look only at your side and just brush off the another side of the argument, it doesn't really help anything. So let's go ahead and look at some of these and what we see with a flat Earth. What might a flat Earth look like? Well, we know that there cannot be an edge because we know we don't fall off the Earth no matter how we travel over the Earth. So one thought on this is that there is an ice wall at the edge. So we see the Earth here, North Pole at the central region. And then we see the various continents and things are stretched out so that the Antarctic region becomes a great ice wall around the edge of the disk. So what keeps the oceans from spilling off the edge of a flat Earth is this impenetrable wall of ice. So this is one way, we have to be able to circumnavigate around the world. We have to be able to travel around. As we know, we can go all the way around the Earth. But this is a way to do that without actually ever falling off or reaching an edge. Now, what is the evidence for a spherical Earth? Well, we've already talked about this a little bit. We gave ideas that even the ancient Greeks knew that the Earth was spherical. So we're going to look at a couple things here, and this is not a complete list. I'm only doing a little bit in this lecture we're covering here. So we have observations from spacecraft. We have observations of lunar eclipses over the centuries. We have observations of the stars and constellations, looking at things like the seasons and the sun, and gravity. How does gravity work in a flat Earth? So let's look at each of these briefly in turn. So let's look first of all at observations from space. So here is an image taken by Apollo 17, the last mission to the moon, showing the Earth as a sphere. And we can see that here that the Earth is very clearly spherical. And in fact, you could watch over time and watch the Earth rotate underneath you. Of course, the only people who saw this directly were, of course, the astronauts who traveled to the moon and back would be able to see that. However, far more people have seen the Earth from low Earth orbit, and that is from things like the space shuttle, now retired, or the International Space Station. And while they cannot see the entire Earth, you can certainly see the curvature of Earth from this level. Now you can't see the curvature of Earth when you're down lower, because the curvature is so small. You wouldn't notice it even looking out on very large distance, even look at large distances when you're on the surface of the earth. You have to get up far enough above it to be able to begin to see that curvature. But here you can clearly see it in the image of the International Space Station. Now, the flat Earth interpretation is really that most of what NASA has done is fake, that space flight is not possible. And the images like these are completely faked, and that no one has gone into space. So essentially refuting all of this by saying that this simply cannot happen. So let's look at something else. Let's look at eclipses. This is one of the things that the ancient Greeks knew. And what they noticed is that during a lunar eclipse, we know that the Earth's shadow is being cast upon the moon. So the moon is moving into and then out of Earth's shadow. And we notice that the shadow is always circular. No matter what, we always get a circular shadow. And you can see that here. If you look at the shadow going in, it always forms a circle as the moon is moving into Earth's shadow. Now, important that it's always, because the only object that will always cast a circular shadow is a sphere. So this is one of the way that the Greeks knew that the Earth had to be spherical, simply because it was always a shadow. If you had a flat disk, depending on the orientation, you would get different elliptical type curves, or even flat lines going through the moon. So you would not get a complete eclipse. So the fact that we always see a curved shadow, circular, is very important and shows that the Earth has to be spherical. Explanation from flat Earth is that it is not the Earth casting the shadow at all. There is another object, a shadow object, which is causing the shadow out in space. And that is what is casting the shadow on the moon during an eclipse. And that is why doesn't have anything to do with the Earth that is causing the shadow. So there's another unseen object that we cannot see that is actually casting this shadow upon the moon. So let's look at the stars and constellations. We note that we see different stars when we travel to different locations on Earth. So if you're in the northern hemisphere, you see the stars up toward the north celestial pole all the time in the sky, and you never see stars toward the south celestial pole. Easily explained, because Earth is in the way. You can't see through Earth to see those other stars. So we also note that constellations in the southern hemisphere appear upside down. Why? Because you're standing the opposite direction. So a person standing on the northern hemisphere is standing one way, has their head going up one way, and they're going the other direction, will make it appear that the constellations are upside down. Orion is a prime example of this. If you look at Orion from the southern hemisphere and you're used to viewing it from the northern, it's going to look wrong to you. Now, the flat Earth explanations here at the stars are actually much closer. So you cannot see the entire sky, that the stars are not at the great distances that astronomers say they are. And the upside down appearance is due to the perspective of this much closer stars. How about the sun and the seasons? Well, we can look at those. The sun would be visible. Wouldn't we think that if the Earth were flat, the sun would either be visible or not visible to the entire Earth at once? So why would we be able to see the Earth? If the Earth is flat, then the sun should be up and everyone should see the sun, or it should be on the other side of the flat Earth and we would never be able to see the sun. So that's one. Here it's the explanation is that the sun is more of a spotlight. It's much closer to Earth. And therefore you have some regions where you simply are not able to see it, that the sun is much smaller than we say, and that they are much closer to Earth. We also note that the length of daylight changes with latitude, and we have different seasons. Now that can be explained by the Earth's tilt as it orbits around the sun and the tilt of the spherical Earth. However, the sun is close and orbits around in a circular pattern, so that we get the yellow line in the summer, the red line in the winter, making the sun more overhead at northerly latitudes and then at southerly latitudes later on. So that the sun would orbit in this path, that it would go from summer to fall to winter and then back again and continue to make this little pattern in its orbit. And that would account for things like the differing seasons, the sun being further overhead and less overhead at other times, and the fact that it is so much closer, meaning that it is not visible from all areas at the same time. So here you would be able to see it in one area like a spotlight, and then as that moved around, you would have other areas become illuminated. Now, let's also look at the shadows. One of the ways that Eratosthenes was able to measure the circumference of the Earth was by shadows cast in different locations and finding that they're different lengths. Now that does make an assumption that the sun is very far away, so that all of its rays come in parallel. But that allows us to make these measurements of the size of the Earth. However, under the flat Earth explanation, the sun is much closer. So the sun is very close to us, and therefore it can be overhead at one part of the Earth, but not the other part of Earth. Now, finally, let's look at gravity. So how does gravity work? Well, we know how gravity works. Gravity would crush a disk into a sphere. Any sufficiently massive object will crush itself into a sphere. And gravity always pulls down regardless of your position on Earth. So how does gravity work under a flat Earth explanation? Well, first of all, gravity is much weaker. So gravity is not able to crush the Earth. And another thought is that the Earth can be accelerating upwards to simulate gravity. Now, this actually is one of Einstein's postulates, that there is no way to tell the difference between a gravitational field and a constant acceleration. However, if we imagine Earth accelerating up at a rate to produce gravity, it would be after a year, it would reach the speed of light. And that's ignoring relativistic effects. It would take it just under a year to reach the speed of light, accelerating at 9.6 meters per second squared. And that would mean that we would be traveling incredibly fast through the universe. How have we been doing this for centuries and centuries? Now, with relativistic effects, you would never actually hit the speed of light, but we would be traveling at an incredible velocity. After doing this for just a few years, we'd be traveling at 99% of the speed of light after just a few years. So how would we be moving this quickly through this, and how would that affect our observations of the stars? So let's summarize a little bit here. And what are some of the explanations? Again, some of them are a complete disregard for scientific observation. So ignoring anything that NASA does. So we have to say that anything NASA did over the last 60 years has been faked. And we also have to believe that the distances that I give you in this class for things like the sun and the stars are wildly incorrect. So let's go ahead and finish up as we do with our summary. And what we see is that the flat Earth proponents make a number of explanations to explain how the various astronomical observations can be explained under a flat Earth. To be fair, many of these do involve a disbelief in observations made by NASA. So you do have to discount everything NASA has done and many observations made and measurements made by astronomers, especially in terms of distances and how far away things are. And at least in my opinion, the scientific evidence for a spherical Earth is overwhelming. And we have known this since the time of the early Greeks. So that concludes this lecture on the Flat Earth Society. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.